All right, so let's move into 3 dimensions. So if we think back to 2 space, the Cartesian plane, the rectangular coordinate system, we graphed lines and all we needed were 2 points to graph a line. Well, and we represented those points as ordered pairs, an X and a Y value. Well, now we're moving into 3 space, the 3-dimensional coordinate system. And in the 3-dimensional coordinate system, we have 3 variables. So now we have X, Y, and Z when we want to write a point. We write a point in 3 space as an ordered triple, X, Y, and Z. Now, it's kind of difficult to represent 3 dimensions on a planar surface on a 2-dimensional sheet of paper. So it's kind of difficult, but we're going to do our best. And we're going to plot points in 3 space, ordered triples. We've now introduced the Z variable, the Z axis, which is going to be your vertical axis. And when we want to write a plane, to write the equation of a plane, it's going to be AX plus BY plus CZ equals D. I've just introduced another variable, and therefore I have a little bit more in the equation, and we want to state that A, B, C, and D are just elements of the reals. So they're just real numbers, okay? So let's talk about how we're going to graph points, ordered triples in 3 space. So if I were to give you point A, and again, I know this represents X, Y, and Z, let's do our best to understand how we're going to represent this on a 2-dimensional surface on this piece of paper. So notice that your X-axis is kind of coming towards you. The X-axis is coming towards you and going back behind the piece of paper. The Y-axis is what we used to look at as the X-axis in 2 space. And the Z-axis is now vertical. So we've introduced this axis coming towards you, X, and going back into space. So if I were to plot this ordered triple, I'd go +3 in the X direction. So I start at the origin, and I'm going to show how I'm traveling, although you don't necessarily draw the path, okay? But to help you visualize it, I will draw it in the first one. So I'm going forward 3, 1, 2, 3. From the origin, I've gone forward 3. In the Y direction, I'm going -2. So I'm not going to the right in the positive direction. I'm going left 2 in the -Y direction. Now, since I'm on a surface, it's kind of hard to see, but this is kind of, you know, coming out like this. So if I were traveling 2, I would go 1, 2. So I'm going 2 in the -Y direction. And then I'm going in the Z direction, +1. So I'm going up from here 1. These are coming out here. So I mean, it's very hard to see in a 2-dimensional space. So where is this point? If I were to graph this point, 3, -2, 1, it would be here. That's point A. So again, you don't necessarily draw the path, but right now for you to see it, I'm drawing it. Now let's look at B. Let's say I want to graph B. Again, this is X value, Y value, and Z value. And I'll draw the path, but you don't need to. If you want to do it on the quest to help you, that's fine, but make sure I know where that point is. Label that point. So from the origin, I'm going +2 in the X direction. I'm going -1 in the Y direction, and then I'm traveling 1, 2, 3 in the Z direction, -Z direction. So that is my point B. Okay, now let's try C. Let's try to graph C. From the origin, where am I going? In the x direction. I'm going -1, right? So I'm going back on the x-axis. And then am I going left or right? No, because y is 0, so I'm not going left or right, but I am going, what? Up 2, so 1, 2. So there is C. Let's try D. From the origin, where am I going? One where? Forward. Beautiful. And then I'm going where? Three to the right. Remember, these are like this, right? Because I'm on this plane. So I went 1 forward, and then I went 1, 2, 3 to the right. And then from there, in the Z direction, down 1, right? So it's about there. Now, these aren't going to be perfect, but, you know, if D is here, it's correct. If it's way up here or something, then I know you did something wrong. Okay, let's try one more. From the origin, where am I going? I'm not going forward or back because x is 0. Then I'm not going left or right because y is 0, but from the origin, I am going up 3. So there is E.
Dr. P, I have a question.
Yes, ma'am.
Hypothetically, you could label the axes any letter, right? And you would move it.
Absolutely. And I could rotate this, and you're bringing up
Okay.
a very good point. You're bringing up a very good point. Because
So is that why we label our axes?
Yeah.
Okay.
That's one reason. That's one of the many reasons you do. Okay, what I would like to do is I would like to open Desmos. I mean, not Desmos, sorry, Geogebra. Okay, so Geogebra is going to allow me to graph in 3 space. So let's go ahead and open up Geogebra. So let me switch. This is going to be beautiful to allow you to graph in 3 space. So let me come over here and share this screen. Okay.
Dr. P, you're muted.
Can you hear me now?
Yes.
Okay. All right. Thank you. Thank you. Thank you. Thank you. Okay. So if you go to Geogebra and you graph in 3 space, you can show the grid if you want to see it. I can actually change and label my axes so I don't get confused. So I can choose to label my axes. So I'm going to go ahead and do that. I'm labeling my axes. That way I can see what's going on. So I can rotate this. So X is coming towards you. So if I wanted to look at the point 3, -2, 1, remember we came forward 3, we went back 2, and then we went up 1. So you can actually, you know, play with it. This is beautiful. 3 space. I love it. Now I can plot another point. I could say, oh, I want to see the next one, 2, -1. -3. So there's that point. We went forward 2, we went back 1, and then we went down 3. So this allows you to kind of better visualize in 3 space what these points look like. Are there any questions about plotting points? Okay, let's go back and move forward then. We've plotted a point, but now we're not going to be necessarily graphing lines. We're going to be graphing planes. So let's go back to our notes. And let's talk about graphing planes. So if you recall, the graph of a linear equation in 2 variables would be a line. In 3 space, the graph of a linear equation in 3 variables is a plane, because a plane is defined by 3 points. Now, if you think back, if you were given an equation, a linear equation in 2 variables, and you were asked to graph it, if you were given that equation, you could always find the intercepts. You can do the same thing by graphing a plane, a linear equation in 3 variables, by finding the 3 intercepts. It's the same concept generalized to higher dimensions. So how do we find our intercepts? Well, to find the x-intercept, you set y and z equal to 0. And then to find the y-intercept, you set x and z equal to 0. And to find the z-intercept, you set x and y equal to 0. What if on an assessment, like an upcoming test, I gave you this linear equation in 3 space and I asked you to graph it? Let's talk about how we're going to graph this. So the first thing you're going to want to do is find your intercepts. So let's go ahead and talk about how we're going to find, let's say, the x-intercept. If I wanted to find the x-intercept, I'm looking for the x value for when y and z are 0. So I'm going to go to the original equation, and I'm going to set y and z to 0. And what do I get for x? -3. So I now know my x-intercept. And you're going to write your x-intercept on that quest as an ordered triple. If you do not write it as an ordered triple, you got a problem. And you're not getting it right. So I could plot that. I could go ahead and plot that point. From the origin, where am I going to graph the x-intercept? 3 to the, this is -3. So I'm going 3 in the negative x direction. So I'm going back 3. So there's my x-intercept. It falls on the x-axis, and we expect that to be true for intercepts. Now let's go ahead and solve for the y-intercept. Remember, for your y-intercept, you set x equal to 0. You're solving for y, you set z equal to 0. So I go back to the original equation. Oops, that's a minus. And I get -3y equals -6. So y equals y is 2. So my y-intercept is in fact 0, 2, 0. So how am I going to graph that y-intercept? Where am I going to go from the origin? To the right 2. Okay, and last but not least, let's go ahead and graph our z, or find our z-intercept. Set x equal to 0, y equal to 0, and solve for z. And what is z? -6. So here is my z-intercept. So I write the intercept as an ordered triple, and I plot it. So from the origin, where am I going to plot the z-intercept? Down 6. Now, what on earth do I do with those 3 intercepts to graph that plane? Well, I'm going to connect them to the best of my ability to show this little triangle, right? And then I know that a plane is going to go through that. So how do we kind of denote that? We just draw this beautiful little plane and show that it contains that little piece. So this is just, you know, to demonstrate that I've connected my intercepts and I have a plane. Okay, let's try another one. Oops. Here we go. I want to graph this plane. I'm going to graph this plane by finding my intercepts. My x-intercept. What is my x-intercept? Four, 0, 0. So from the origin, where am I going? To plot the x-intercept. Forward 4. Yeah, there's my x-intercept. Now let's graph our y-intercept. What is my y-intercept? 0, -1, 0. And where am I going from the origin to graph my y-intercept? And last but not least, let's graph the z-intercept. Let's find it. And what is z? And so from here, where am I going to graph it? Up to. Now, here I'm going to try to graph this. Oh, well, that's horrible. How am I going to graph that plane? That's kind of a disaster to graph, right? So let's go back to Geogebra, and let's see what it looks like on Geogebra to see if I can better recognize what's happening. So we go to Geogebra, and instead of these points, well, let me go. Well, let me plot. Oh, I think I'd like to plot my points. Let's plot those intercepts. So the first intercept we said was 4, 0, 0, right where we expected it, right forward in the x direction. Now let's plot the y-intercept, 0, -1, 0. Okay, that's exactly where we had it on our graph. And now let's go ahead and plot the z-intercept, and it's 0, 0, 2. Now, look at that. That was very difficult for us to see in 2 space. But what if I want to draw the plane that passes through that? Well, you can actually tell it to graph the plane through the 3 points. But let's go ahead and write the equation of that plane that we were given. X minus 4y plus 2z equals 4. And look at that beautiful plane going through those 3 points. You see that? That's lovely. That's fantastic. That's absolutely magnificent. Look at that plane. So it's kind of hard to see in 2 space, but coming to Geogebra, we can actually, you know, manipulate it a little bit better. So I highly recommend to make sure that you know what you're doing, right? So again, you can play with this. You can actually connect the points. If I wanted to connect the points, well, you know, let's see. Look at all these things we can do. So I want to draw the plane. It's going to be the same thing, right? If there's the plane passing through those 3 points. How do you get the plane? Well, I typed in the equation. So you can type in the equation of the plane, or you can go to this symbol with the circle intersecting with the triangle, and you can say draw the plane through the 3 points, or you could come down to, well, you know, you're going to do your best to draw it. So like, for example, on this one, it was a little bit easier to draw. This one is very hard, right? You just do a little sketch. Yeah, you plot the 3 points and then you show the triangle and you shade it and then you kind of show that the plane goes on from there. There's no exact way to do it other than plotting the 3 points and kind of shading the little surface that is created by it. Okay, let's keep going because now we're going to solve systems. We're going to solve systems. So let me stop broadcasting here. And let's go back to our notes. So we can have a system of 3 equations in 3 variables. Now there's many different ways that these planes can be related in 3 space. So these 3 planes can be related in 3 space in many different ways, right? So we're actually going to look at that and then let's go ahead and talk about it a little bit. So if I have a system of 3 equations in 3 variables, let's talk about how we can expect these to be related. Now in 2 space, we talked about how the lines could be the same line, how they could be parallel lines, or the same line, parallel lines, or they could intersect at one unique point, right? Well, the same thing is true in this instance, but now we have planes. So they can either be the same plane, right? All 3 could be superimposed, or we can have a line where 2 planes at a time intersect, or we can have a point, right? But I wonder what those other 2 options are. There could be no intersection, right? Or in beautiful cases, we can look at all of 3 space as being a solution set. And we'll talk about these, but these are like the possibilities that we can work with. So let's talk about the process of solving a system of 3 linear equations in 3 variables. So what is this equivalent to? This is equivalent to finding the points of intersection of the 3 planes. Now, remember, we use the term consistency if the system has at least one solution. If one solution exists, the system is consistent. But there's different ways that they can be consistent. Remember, they can be consistent independent, or they could be consistent dependent. Consistent independent means all 3 planes intersect in exactly one point. There's one solution, and the solution is in fact an ordered triple. So that would be known as the origin, right? If we were looking at it. So if you have a consistent independent solution, all 3 planes intersect at one point, and the point is represented as the ordered pair. The ordered triple. Now, you can also be consistent, but you can be consistent dependent. What does it mean to be consistent dependent? Well, they have infinitely many solutions. And we can say that all 3 planes intersect either in a common line, because we know there are infinitely many points on a line. So all 3 points, if we want to visualize how 3 planes can intersect in a line so that this entire line is the solution set, or they can coincide, overlap, and so all the points would be every point on the plane. So where do you recognize that when you have infinitely many solutions? Well, when you're solving a system, if you can get a unique X, Y, and Z value, a unique value for X, Y, and Z, you have the point where the three planes intersect. However, if you're algebraically solving a system in three space, three equations and three unknowns, and you get a true statement that is true at more than one ordered triple, you have infinitely many solutions, then you have to figure out which instance it is and define the solution that way. So consistency means, again, a solution exists, and then you have to figure out whether it's consistent, independent, or consistent, dependent, and more specifically, how you would represent the solution set for a dependent system. Now, in addition to it being classified as a consistent system, we could also use the term inconsistent to describe a system. And an inconsistent system has how many solutions? None. No solutions. No solution for an inconsistent system. So let's think about how those three planes can be related in three space for there to be no solution. Well, all three planes can be parallel, right? Here, these three planes are parallel. They never cross, so there's no solution. Or I can have two planes that are parallel, and who cares if that third plane passes through it? Two of them never intersect. So there's no common point or set of points. And the third instance could be, well, two at a time could intersect. But if two at a time intersect, no solution exists, and there is not a single unique point or set of points that is satisfied by all three planes at the same time. How do you recognize this when you're solving a system algebraically? You get a contradiction. As soon as you see a contradiction in your system, when you're trying to solve it, that clues you in, there is no solution. So again, solutions to a three-dimensional linear system in three variables is an ordered triple, if it's unique, solution that satisfies each of the equations. You should be able to substitute in that ordered triple into every single one of the equations in that system, and it has to make a true statement. It has to make an identity. So I may give you a system, and I say verify or determine if the ordered triple I have given you, meaning an X, a Y, and a Z value, is a solution. You're going to come into each system, each equation rather. So I'm going to label my equations, and I'm going to come into my first equation, and I'm going to substitute in that X, that Y, and that Z. I'm going to come into my second equation, and I'm going to substitute into that X, that Y, and the Z. And then I'm going to come into the third equation, and I'm going to substitute in for that X, that Y, and that Z. If it doesn't satisfy all of them, it is not a solution. It must satisfy all of them. So let's go ahead and do that. Let's substitute in -1 for X, 2 for Y, sorry, I'm trying to color coordinate this for you. -2 for Z, and let's see if we get a true statement. So I have -1 plus 4 plus 6 equals 9. Is that true? Yes. So don't get excited. You can't say yet that it's a solution. We have to do substitution in every single one of these equations. So let's go ahead and do the second one. I'm going to substitute in -1 for X. I'm going to substitute in 2 for Y, -2 for Z, and see if it equals -8. Does it equal -8? Yes, it does. Again, we still cannot say it's a solution. It has to satisfy all of the equations. Because remember, it has to be on every single one of those planes to be a solution. So I'm going to do the same thing. And I'm going to substitute in X, Y, and Z. Be careful of your minus signs because that can trip you up. Does it satisfy the last system, the last equation? Yes, it does. So only at this point we can say -1, 2, -2 is a solution to the given system. But you would have to show me that it satisfies all three of the equations. If any of these, I'm looking for all of this. It's not enough to say it satisfies one. It has to start, if any one of these has produced a contradiction, it would not be a solution. It would not fall on those planes. Okay, so that's fine. We can verify a solution. We can maybe classify the systems if necessary. Since it does have a solution, how would I classify this system for kicks? And it has one solution. If you were to classify it. Okay, let's talk about how to algebraically solve these. There's a process. And really, you know, it looks intimidating, but if you can reduce the system to 2 equations and 2 variables, then you know how to solve it. That's what we're doing. That's what we've been doing. So I'm going to reduce the system of 3 equations and 3 unknowns by eliminating one of the variables. Then I'm going to solve the reduced system and substitute those values, substitute the values into previous equations, and then substitute both those values into the original equation. And then at the end of the problem, make sure you check your solution by substituting in the point if you got a unique order triple into each of the equations to verify. There's no reason that you should submit an order triple and say that's the solution when if I were to go back and substitute, it wouldn't work. So let's look at an example. Okay, and let's walk through how we want to write our work. So I've given you the steps, but I'm not going to give you the steps on the quest. You're just going to be given the system. But let's talk through the steps. So the first thing we want to do is we want to take the system of 3 equations and 3 unknowns and reduce it down. We want to eliminate one of the variables. Now, it does not matter what variable you say you're eliminating to begin with. It doesn't matter. Now, sometimes there's an easier way to do it, but it doesn't matter. So I'm going to first label each of my equations. Because if you do not label everything on that quest, there is no way for me to tell what you're doing, and there's no way for me to give you partial credit. So I've labeled my equations, and I need to determine which variable I want to eliminate. Well, personally, I see in the second equation that little minus y, it has a -1 coefficient. That's going to be my clue to maybe eliminate y. Okay? Again, it doesn't matter what you choose, but there's sometimes an easier way, right? So we have to be careful how we're choosing it. No matter how you choose your which variable to eliminate first, you're going to get the same answer as long as you do your algebra correctly. Okay, so I'm going to choose 2 equations at a time. So I'm going to choose equation 1 and 2. So I'm going to eliminate y using equation 1 and 2. And then I'm going to eliminate y using equation 2 and 3. I'm exploiting equation 2 because of that -y. So let me rewrite my system based on the equations I have chosen. Equation 1 and equation 2. And then I've chosen equation 2 and equation 3. So my first step is to state what you are eliminating, state which variable you're eliminating. So I know what you're trying to do. There's a question. Blaine. Did you have a question? Your hand's up. No. Okay. Just making sure. All right. So tell me, the first thing you do is tell me the variable you're eliminating, label your equations, and then show me which sets of equations you're using. You're going to choose 2 at a time, and you're going to see how it reduces. Now, I said I want to eliminate y. So I have to ask myself, what do I have to do to one or more of these equations so that I can multiply maybe something by one of the equations to get opposite coefficients? Why do I want opposite coefficients? Because if I add the two equations together, I want to be able to eliminate y. So what do you think you might want to do to one of the equations so that if I were to add them together, the y would be eliminated? Anybody have any ideas? I have a positive 2 here, and I have a positive 2y and a negative y. What might I do to the second equation so that I get those to be opposite coefficients? Multiply by 2. Okay. Now, at this point, if you want to rewrite the system, you can. You don't have to if you want to do it in your head, you know, but the more you write, the better it is for me to give you partial credit. So I didn't do anything to the first equation. I multiplied the second equation by 2. So my new second equation is going to be 4x minus 2y plus 6z equals 8. So now my goal was to eliminate y. Did I eliminate y? Absolutely. My new reduced equation is this. And I'm going to call that equation 4. Now I'm going to come over to the second set of 2, and I'm going to ask myself, what am I doing to one of the equations so that if I were adding the 2 together, I could eliminate y? I need opposite coefficients for y. What am I doing? Beautiful. Multiply the first equation by negative 3. So I'm going to rewrite this and get negative 6x plus 3y minus 9z, equals negative 12. My second equation I didn't change. Now if I were to add the 2 together, do we get this? I'm going to call that equation 5. I have now taken my system of 3 equations and 3 unknowns and reduced it to 2 new equations in 2 variables. So let me rewrite my new system. So that was equation 4, that was equation 5. That's kind of ugly. Look at that new system. Now you tell me you don't know how to solve that, right? I can use the same process. I can use elimination. I could use substitution. It doesn't matter. But I'm going to use elimination. And what variable do you think you're going to want to eliminate now? X. I would eliminate X. So if I want to eliminate X, I'm going to keep my first equation alone. Not change it, but what am I doing to my second equation so that I can eliminate X? Multiply by 7. I agree. Okay, I'm going to rewrite my system. First equation didn't change. My new second equation is negative 7x minus 28z equals what? Negative 91. And if I were to add these two together, my goal was to eliminate x, and I did. And what do I have? I have negative 18z equals negative 72, right? Bless you. What would I do next? So I divide by negative 18. And what do I get for z? Positive 4. Yes. Now, don't even think you're done. I mean, you know, remember, if I'm trying to find a solution, a unique solution, then I'm looking for an x, a y, and a z. An x, a y, and a z. So now I have to solve for the other variables. So what on earth am I going to do with this z equal 4? I'm going to come back here, and I'm going to substitute in for z. Doesn't matter where I substitute in. And I'm going to be able to get x. So I'm going to now back substitute. And I'm going to substitute z equals 4 into either equation 4 or 5. It doesn't matter. And solve for x. Which one would you like to substitute back into? Doesn't matter. You want to do equation 5? Okay. So I'm going to take equation 5, which was negative x minus 4z equals negative 13. Negative x minus 4 times, and we know what z is. We just found it. I'm solving for x. So what is x? Negative 3. So I now have x and z. So with x and z, I can now substitute x equal negative 3 and z equal 4 into any one of the original equations. I don't care which one you do. Doesn't matter. It has to satisfy all of them anyway. So if I'm solving for y, maybe I'm going to choose equation 2. But it doesn't matter. So I'm substituting in negative 3 for x. I'm solving for y. And I'm substituting in 4 for z. So far, so good? Okay. So what is y? Y is 2. So yay, I'm excited. I have a solution, but I have to write the solution, in its entirety. So if I want to write the solution in its entirety, I would say the solution is the ordered triple: x value, negative 3, y value, 2, z value, 4. And I could check it by substituting that into equations, correct? Shall we do another one? Yes, because we love it. It's exciting. 3 equations, 3 unknowns. Here we go. Equation 1, equation 2, equation 3. Now I'm looking at those and oh gosh, take your pick. What do you want to eliminate? Anybody have a preference? Z? Okay, so I'm going to eliminate Z, if I heard you correctly, Mia. So I'm going to look at equation 1 and 2, and then I'm going to look at equation 2 and 3. And then equation 2 and 3. So please do write what you are solving, how you are solving these. State what you're eliminating, rewrite your systems. Help me give you partial credit if you make a careless error. If you do not show me work, I cannot find your mistake. Okay, so here we go. Looking at equation 1 and 2. What's happening? We're eliminating Z. What am I going to have to do? What? Multiply the second equation by 2, right? Because we're trying to eliminate Z. So I'm going to rewrite my system because I like to show all my work. And this becomes 6x plus 4y plus 4z equals -6. Then I'm going to add the 2 together. Z is gone. That was our goal. Yay. What? Did I write something wrong? Oh, this is a 3. Oh, thank you. Let me erase that. Thank you. This is a 3. So that becomes 6. It's not going to let me erase that. The poopy thing. That's fine. And that's going to equal -3. So that's my equation 4. Okay, now let's look at our second set and see how I'm going to eliminate Z. What do I have to do? I love it. So we multiply the first equation by -3 and the second one by 2. I could have multiplied the first one by 3 and the second one by -2. I'm going to get the same answer. Either way. Rewrite the system. So that's -9x minus 9y minus 6z equals 9. And then -4x plus 10y plus 6z equals 6. And check everything because I can look how easy it was for me to write the wrong number down. My gosh. But I would have lost only 1 point because I showed all my steps. All right, now I'm going to add them together. And what do I get? -13x plus y, z's are gone, equals 15. That's my equation 5. So I have a new system. Consisting of equation 4 and 5. What variable do you want to eliminate? Next. Okay, we'll eliminate y. So to eliminate y, what do I have to do to one or more of these equations? Okay, so I'm multiplying the second equation by -4. So let me rewrite my system. I have 11x plus 4y equals -3. And then I multiplied by 4. So what's my second equation? 52x minus 4y equals -60. Yeah. And then if I were to add those two together, 63x gone equals -63. So what do I now know? X equals -1. Okay, so where am I going to use that? What am I going to do with that? Yeah, I'm going to come back over here and substitute into one of these equations. Anybody have a preference? No? Okay, I'm going to do it in for 5. It doesn't matter. And I'm substituting in -1 for x. That gives me 13 plus y equals 15. So what is y? 2. And I have x and I have y. What am I going to do with that? One of the original equations. I'm trying to solve for z. Doesn't matter. Do whatever you want. I'm going to do it in equation 1. But it doesn't matter. So 5 times x, which was -1, minus 2 times y, which we found to be 2. And I'm solving for z. Ugh. So then I have -4z equals what? What? Oh my goodness gracious, I'm having all sorts of issues today. It doesn't let me erase. So let me just make that 5. So that's 9. So that's going to be what? 12. So what is z? And I have a unique solution. So my solution is -1 to -3. And you need to write it as an order triple if it's a unique solution. And how would I classify that system? Consistent, independent. Okay, I'd like to work the word problem with you, or at least set you up for the word problem. So you have this example for Wednesday. In addition to the worksheet where you are graphing, so you have a 5.2 worksheet, make sure that you turn that in. You're going to upload it and scan it and upload it and submit it. Do Wednesday. But this problem you're going to do for Wednesday, and we'll discuss it when we come back to class. And then this problem you're going to do for Wednesday, again, solve it and then classify each of these systems as well. If you want even more practice, there it is. But let's talk about the application. Let me get you started on the application so that you can finish this one as well. And we'll discuss all of these on Wednesday, and then you'll be prepared for the quest on Thursday. So a track relay team scores 5 points for finishing first, 3 points for finishing second, 1 point for finishing third. Lynn's team scores a total of 30 points. Write a linear equation in 3 variables to represent this situation. So the first thing I want to do is define my variables. Oops. I'm going to let F equal, I'm going to let F equal the number of races finished first. Then I'm going to let S equal the number of races finished second. And I'm going to let T equal the number of races finished third. And I know I scored a total of 30 points. So how on earth can I represent this as a linear system of these three variables? I mean, a linear equation of these three variables. I have 5 points for every time I finished first, plus 3 points every time I finished second, plus 1 point for every time I finished third. And how many points did I get? 30. You see how I arrived at that? Okay, so there's my linear equation in those three variables. Now the question is, if Lynn finished second in second in 6 events, no, third in 6 events. No, sorry, I can't even read this teeny tiny print. Hold on. She finishes second, so that was green, in 6 events. Third in 2 events. I want to know how many events she finished first. So I'm solving for F. And I can substitute what in for S? 6. And then what for third? And that equals the 30 points that I earned. Oh no, I only get, sorry, I'm having so many issues today. She finished third in 2 events, so she only gets a point for finishing third. So what is F? So we can say that Lynn's team finished first in 2 events. Okay, so what do I want you to do for Wednesday? For Wednesday, I would like you to do example 5. Solve it, classify the system, do example 4. Solve it, classify the system, and do the worksheet. Okay? These other ones are just for fun, extra practice. I gave you extra practice, but you don't, that's just for you. So finish those 2 examples and the worksheet for Wednesday. And then Wednesday, we will go over those 2 examples and start preparing for the quest on Thursday. Are there any questions? The worksheet is on modules, but it's also in that top tray. But you'll submit it in modules. Okay, so if you want to go ahead and work those 2 examples now, we still have time. I'm going to write the answers and work them out. Don't look until you've done them, but do those 2 examples now. Why not? What are you waiting for? Of course you may. I'm going to do the 2 examples and feel free to check them as you work them and see if I made any mistakes. Careless errors. So you're working them and I'm working them. first step's been done for you on example 4. Do you notice that? The y has already been eliminated.
The worksheet by the end of the period, or
I'm sorry?
do we turn in the worksheet by the end of the period, or?
No, it's due Wednesday.
All
The
right.
worksheet is due Wednesday, and I'm going to push the My Math Lab probably till Thursday. I haven't decided. It depends on or maybe Wednesday afternoon. No, it should be already due Wednesday afternoon. So that'll be fine. You should be able to do it by Wednesday afternoon.
All right, thank you.
Mm-hmm. Did we get the solution to number 4? That one was not bad. Mm-hmm. The intercepts. Mm-hmm. Mm-hmm. Mm. Well, there's only one plane, right? There's only one plane. You plot the 3 intercepts, and then you connect the points and get a plane. These were interesting. These were interesting problems. Very interesting problems. Did y'all get them? Did y'all do the last 2 examples? You want to check your answers? I've already done them. Okay. For those of you who are not in the room, if you want a hard copy of the worksheet, it's in my room. Otherwise, you can get it off Canvas. It is due Wednesday, as well as the My Math Lab. If you have any questions, look at these answers. The video will be posted on YouTube for the answers to these last 2 examples. So we are going to review, and I'll give you time to do more practice problems, and then we'll have a quick little review in class on Wednesday online. And then your quest is Thursday, and we will meet in the library for your quest. Library for quest. Okay? I'm going to end the meeting, so if you have any questions, maybe I'll see you in tutorials. Maybe I won't. Bye.
Thank you.
You're welcome.